Hello everyone, thank you for watching this video. This video was created out of a project that a group of us students from Liberty University are working on dealing with human performance. My name is Corey Messer. I'll be speaking in this video, and then also a few other people that will be speaking is Matthew and Cal. They'll be touching a little bit on the philosophies of human performance, and then also Katie, myself, and Ashley will be talking and addressing about the textbook theories on human performance.
So to begin looking at the philosophy of human performance, it's important to ask yourself, what exactly am I studying? So we've laid out here 4 aspects of human performance that we like to study. The first is speed, and speed is measured by the time it takes to complete a task. We like to think of speed as miles per hour when we're driving a car down the highway. How fast, how many miles can we go in 1 hour? Well, when speed is talking about human performance, we like to ask things like how many cycles per minute we can go through, how long it takes a human at a workstation to complete their task. The second of these 4 attributes of human performance is accuracy. Accuracy is measured by observing the number of errors over a unit of time. An example of this could be the defects per minute. So if there's somebody working on one machine and they output 100 items per minute, and 2 of them are defects, that's something you can write down and analyze later. Maybe somebody can lower the amount of defects, or if somebody has more, you probably don't want them working there. A good rule of thumb is that the less errors there are, the greater the accuracy is. The third aspect is consistency, and this deals with both speed and accuracy, and it's measured by the standard deviation of time to complete a task in the case of speed, and the standard deviation of error over a unit of time with accuracy. And the fourth aspect is learnability. Learnability is measured by the time it takes the average person to achieve proficiency with a particular task or piece of equipment. Basically, learnability is just how long it should take somebody on average to get familiar with a piece of equipment and be able to start using it efficiently or with a certain task.
So now that we kind of understand some of the aspects of philosophy, we're going to look at of human performance. We're going to look at why we study human performance from a philosophy standpoint. So first, you want to identify an optimal and feasible method for completing a job when several options are available. We would love to find the optimal method, but first we just need to find a method that works. We need to find a method that interacts with the human employee, however we're going to get the job done. We need to test and prove that we're actually going to be able to complete the job. Next, we want to look at evaluating our devices, machines, materials, and or objects, and seeing how they interact with humans. That would also apply vice versa, how humans interact with these devices. Some of the things that we need to know and reasons we study human performance is how can we mold machines to best be used to the human ability and the human body, and then also how inclusive should the machines and objects be so that the human does not get bored, and different things like that that actually use enough of the human to make it a worthwhile job. Also, we study human performance to prepare and plan for effective production operations. This includes predicting our production costs so we can prepare for the future, and we also want to identify areas of wasted potential.
So now we're going to move on to textbook theory. So we're going to first talk about synthetic data systems. These synthetic data systems allow prediction of performance without making direct measurements on an operator performing the task. So we would be analyzing a task analysis instead of actually watching the task be done. We have a couple different types. We have motion time measurement, also referred to as MTM. This is a predetermined motion system that is used to analyze the methods used to perform any manual operation or task to set a standard. These activities would be like reaching, moving, turning, things like that. Some of them include each other. So when you reach to grab something, you'll be doing both reaching and grasping and applying pressure and all that. So this system does that. Next, we have work factor system. This is similar to MTM, except that it assumes the operator has good skill and effort, which motion time does not. It's about 20% faster than MTM. Work factor system establishes difficult movements. So it will analyze you moving something and being careful of it because it's fragile, steering to a target, or obstacles around the area to have to move an object. Then we have Mento Factor System, which falls underneath Work Factor System. This one will analyze the mental tasks. So for recalling, you'll be recalling a memory, and the Mento Factor System will contain 12 of these mental tasks.
Standard data systems can be used to predict human performance directly or to determine general performance standards within families or similar products. Examples of product families could be the bending of a steel iron, where the jobs differ by the size of the angle iron, and then also like the bending area. And then formula development. Here we have to develop a formula that accurately predicts performance times or also errors. This formula will be a function with x1, x2, as many variables as needed. And these variables, they're going to differ for each product that is going to be modeled. Typically, variables include dimensions, surface finishes, number of corners, back in the bending of the angle, for example. And then also, in order to develop a formula that fits the need of model users, there are some general principles that should be followed. And these general principles really help guide in the development of the function and the formula that you'll be using to model these different systems. Now, some of the general principles I have here listed, they all range in how to create and to somewhat simplify this model and give a direction of where the function needs to go. For instance, you'll want to minimize the number of variables in a equation, and then also each variable should have an obvious effect on the performance time or errors. Variables should be distinct, very one at a time. You don't want overlapping variables. Variables also should be easily found in the projects that you're doing. So if you have maps or if you have diagrams of people, there should be like weight from these people that will go directly to the variables. Format the variables so that all of the same directional effects also have the same occurrence on performance. And then also, you're just going to want to start simple. You want to keep the most important variables in the formula and also add variables that improve the predictive ability of the formula.
And now on to cognitive simulation. So cognitive simulation is cognitive engineering, which provides several approaches for tasks with significant cognitive content. So this will incorporate descriptions, measurements, and design. So there are different types of cognitive modeling. We're going to review 5 different types, and the first category is to provide time estimates of primitive tasks, which this is simply called the model human processor. There are 3 different processors incorporated here. There's the preconceptual processor, which is the visual version or the visual portion of the process. And then there's the cognitive processor, which checks the visual situation, and then also the motor processor, which executes once there has been a visual situation checked. And then moving on to the next 3 different models, which focus on how people use knowledge when they solve problems. The first one is GOMS, which stands for 4 basic concepts for choosing alternative methods, which is the goals, the operators, and the methods, and also to select rules. So GOMS. And then there is the NGOML, which is the natural GOMS language. And this has 3 predefined primitive modeling operators. And first, it is the flow of control, and then second, memory storage and retrieval, and then also primitive perceptual motor actions. And an example of that type of text is in the smaller box at the bottom, where it has the bolded statements and then the 4 different steps. And then also the GOMS text is to the left, which has the different goals listed out, and then also specific languages which explain different tasks that will be achieved after those goals. And then the third focus is the SMESD, which is just simply a task description language, which is the focus is on object-oriented language. And then there is the final category, which is a tool used when developing such models, and that is the SHAP, which helps analysis or analysts perform cognitive task analysis.
So this concludes our video. I want to thank you for watching a little bit about philosophy and textbook theories on human performance. Follow along for future videos as we continue working on this project throughout this fall 2017 semester. Thank you.